Well, hello. So last week we learned about UML, and that is a graphical notation for describing object-oriented systems. The goal of that wasn't really to learn UML or to do anything related to programming. The goal was to take your experience in writing object-oriented programs and try to use that so that it makes it easier for you to design relational databases. So today's the payoff. We're going to start by coming up with some, or rather looking at some mechanical ways of transforming UML diagrams into relational tables. This should always be sort of your first step. If you're faced with a project that you have to build a schema for, and you don't feel comfortable yet, make it working with your schema, making sure it's right, at least come up with a set of classes that would be able to represent that data and then translate those to a schema. We'll see in the coming weeks how to make that even better by taking an existing schema and improving it. But at least that should be your first step. So if nothing else, whatever schema you come up with should be able to represent the knowledge of the world that you're trying to capture. So if the schema doesn't even do that, then it won't work, no matter how beautiful it is. So we have to make sure that it is a working schema. And this is a good way to start with something that will get you that. So anyway, let's get to the payoff. Let's convert UML diagrams to relations. So the strategy is deceptively simple. Here's what we're going to do. Each class that we have in the UML diagram, we're just going to turn that class into a table. Okay, and that table is going to have the same name as the class, and the attributes of the class will just be the attributes of the table. That's that easy. Okay. Now, whenever we have an association, okay, which is one of those lines between two classes, then we'll take that association and turn it into a table. Okay. And what are the attributes of this association? Well, they're going to be the primary keys of the classes that are connected. And the reason is that what the line says is some record here in table A is related to some record here in table B. So what we need in this table that has all of those associations, which is what we're building, is some way of referring to those two records that are related. Of course, we're going to refer to those two records by their primary keys. Now, in addition, if there happens to be any association classes, remember an association class is a class that is related to the association, not to either of the classes on the endpoints, but to the association. So we denote it by having a line that goes to the midpoint of the association line. That all of those attributes in there will actually also make it into the table that has the association. So for example, when we say that this actor was in this movie, and the association also tells us that the actor made so much money for being in that movie, then we would build a table for the association that has the actor primary key, which might be their name, and the movie's primary key, which would be the title and the year, and then as we would add to that the salary, right? So those would be all the entries in that table. So let's take a look. So here is a UML diagram, and we have studios, movies, and stars. Notice that we fixed the cardinality between studios and movies. Okay, so now let's just go through it, and we'll start with movies. We put movies, that's the name of the table, and then we just have the four attributes: title, year, length, and genre. We're paying attention to primary key, so since title and year were identified as being primary key, then we make those in the schema. Pretty straightforward. We'll do the same for stars. We have the name, which is a primary key, and then an address. Studios, coincidentally, has the exact same attributes. It has a name and an address, and the name is the primary key. So that takes care of our first three tables. Now, the remaining two tables correspond to those association, and those are the two lines that we see there. So let's look at the line between stars and movies, and we call that stars in, so that becomes the name of the table. And what it has is the primary keys of the associated classes. So movies is in there, movie title, movie year, that's the primary key. Notice that we prefix the names of the attributes with the name of the table so we know where they come from. Okay, and then we have star name, because name is the primary key of the stars table. So we just took those primary keys and put them in there. Owns, that is the top line, and that is between movies and studios. So again, we have movie title, movie year as the primary keys, and now studio name. So this is kind of our first shot at converting UML diagrams to tables, and you see that it's quite mechanical and actually pretty effective. Okay. Now there is one kind of extra thing that you can do, and this is actually pretty natural when you think of classes, and that is looking at the owns association between movies and studios. If you know the movie, then you know the studio, right? Because there's only one studio that can be associated with the movie. So instead of actually building another table to have that information, it makes a reasonable amount of sense to just say, hey guys, why don't we just add studio name, which is the primary key of studios, to the movies table. That way, if I'm looking at a movie's record, right there I have the studio name, and I can just go in and get information about that studio. This is very similar to taking a pointer and sticking the pointer directly into the record, because when you're at a movie object, then you want to be able to point directly to the studio object. So this is a very common trick, and is a trick we'll use, well, honestly, over and over again. So we won't always create a table for each association. We will look for opportunities, and the opportunities happen where the cardinality is 0 to 1. Okay, we'll look for opportunities to simply add the primary key to the other table so that it points to the 0 to 1 table. In this case, movies points to a 0 to 1 studios table. Notice it wouldn't have worked the other way around, because movies is 0 to infinity. Okay, so it gets a little bit more complicated when we're dealing with subclasses. All right, so here's going to be kind of a running example. We have a class A that has 3 subclasses, A1, A2, and A3. So we're going to have different ways of doing this, okay? In fact, there are 3 ways that are very commonly used. One way is to use a table for each subclass. Okay, so what does that mean? We're going to create a table for A and a table for A1, A2, and A3. Okay, now somehow those tables need to be connected. So A1 has to have all of the primary keys from A. An example of that is, say we had a student as a top-level class and part-time student versus full-time student as subclasses. Well, the primary key of student might be student ID, and then part-time student would also have student ID. Full-time student would also have student ID. And that's important because that's the way that we connect the records of a student across all of these tables, A, A1, A2, and A3. Okay. The other approach is to use a single class essentially for each path to the possible concrete classes. Now, the difference here between these two is a little subtle. And the difference is that instead of having a class for A and a class for A1, we're going to have a class for AA1. Okay? And we'll have a class for AA2 and so on. And we're only going to define classes for, or rather, we're only going to define tables for the classes that are actually concrete, that you can build an instance of. Okay, so if A1 is an abstract class, we're not going to have an A1 table. Okay, if A is an abstract class, there will not be an A table. There may be A1, A2, and so on. Okay, so since we're building a class for, a table for the entire path from A down to A1, what we'll do is we'll put all of the attributes in A and all of the attributes in A1 into this class. So whereas in the one table for each subclass, the attributes for A will be only on the A table. Now they will get pushed down into the A1 table as well. Okay, you can imagine that this is a little convenient, because if I have a record of an A1, I have all of the information about this person or whatever it is. So it is quite convenient. It is a little less convenient in the sense that, for example, if each student is associated with an advisor, but now there is no student class because I moved everything down to part-time student and full-time student, then it's hard to make that relationship really explicit. It's hard to find the information. So, there are trade-offs. All right, then there's option number 3. Option number 3 is traditionally the most favored one, is the one that DBAs tend to gravitate towards. Although object-oriented folks tend to gravitate towards, for example, option 1. But in option 3, what we'll do is we'll have just one table for everybody. And so that table has the attributes of the top-level table A, as well as the attributes of A1 and A2 and A3. Any possible attribute has to be in this gigantic table. Okay? And of course, some of the times the values are going to have to be null because for a part-time student, we may not have records related to, say, memberships to the student club because that's only for full-time students or whatever it may be. The point is that there are fields that are simply not relevant to a record of A1, and so we'll have to add nulls for that. So that's what makes it a little ugly, if you will. But like I said, it's the most well-known approach. So anyway, let's tailor our approach just a little bit because we talked a fair amount about coverage and exclusivity earlier. And what I want to say is that depending on what the coverage and exclusivity is that we're dealing with, it can make some of the drawbacks of some of these different options essentially go away. So then they start looking more and more attractive. So for example, let's say all the classes are disjoint, okay? Then a single class per path is not as crazy as it would sound. If the classes are not disjoint, then what are the possible things that I can instantiate? Well, I could instantiate an A1, I could instantiate an A2, I could instantiate an A3. I could also instantiate an A1, A2, and an A1, A3, and an A2, A3, and an A1, A2, A3. So you see it grows exponentially, right? You know, there's too many possible classes. On the other hand, if they're supposed to be disjoint, then shoot, all I can do is instantiate an A1, an A2, and an A3. So yeah, it still has a drawback. And the drawback is what I told you earlier. If you don't already know that this record is of type A1, you only know that it's an A somehow, then you're going to have to look at it in all the tables, and that's awkward. But at least there's only 3 tables, okay? Now, if you have something that is both complete and disjoint, then the only classes that you need are the leaves. You don't actually need an A, right? So that's kind of nice, okay? And so again, that makes that option look very appealing, okay? Now, otherwise, maybe it's because I've done databases for a very long time. I personally still prefer one table with nulls for the relevant columns. I think that that solves a lot of the problems. Okay, so let's look at some examples. So here is a hierarchy. Notice that we have incomplete and disjoint. Okay, so the disjoint is a good thing. It means that I don't have to worry about mixtures of cartoons and cartoon murder mysteries. Okay, but notice that also what has happened is that I had to create tables in order to make that happen. So I've already, or rather classes to make that happen. I have already paid the price of being not disjoint. Now, if I look at this hierarchy, then let's use the single class approach. You know, this single class goes into a table. So I would have a movies table and title, year, length, and genre, just as before. Notice that title and year are the keys. And now I would have a single class for murder mysteries. And if you look at murder mysteries, that has title and year as the key. It doesn't have a sub-key of its own. So we can just reuse we have to reuse the key from movies. And we also have the other attributes for movies. I have length and genre here because I'm just going to have one class for A1. I'm not going to try to combine murder mysteries with movies. All of the information is in here. That's what it means to use a single class. And of course, we also have the weapon because that is an attribute of murder mysteries. So this has 5 attributes. Cartoons doesn't have any attributes of its own, but it needs to have title, year, length, and genre, which is getting from movies. And title and year are the primary key as before. And finally, cartoon murder mysteries. It's just like mysteries, really. We need title, year, length, and genre, title, year being the primary key, and then we add kind of the local attribute, which is weapon. Okay, so this is what it means to have a single class. All of the attributes are getting pushed down from the root to the leaves of the hierarchy. Okay. All right. Let's talk about a table per class. Now we're not saying a single table per class, just a table per class. So now what's happened is that movies is as before because it's the top of the tree. So you have title, year, length, and genre. Title, year is a primary key. When we add murder mysteries, again, title, year is the primary key. It doesn't have anything to add to that, okay? There is no limit on the number of murder mysteries that can be produced in a year. So it's just title and year. We do not move length and genre down into murder mysteries. And the reason is that if you want to know that, then you're going to ask in the movies table. Okay? There will be a record for each murder mystery in movies and a different record in murder mysteries table. Okay? And depending on what information you want, you will either ask movies or you will ask murder mysteries. Okay? What murder mysteries has is information about weapons. What movies has is information about length and genre. Now, when I look at cartoons, cartoons only has title and year because it doesn't have any extra attributes to add. Okay, title and year are the primary key. So essentially, there's like zero information by being in cartoons. Well, that's not entirely true. There's a little bit of information. The extra information is this movie was a cartoon. Okay, so it's kind of like a set where, you know, the only important thing is that you're in it. All right. Now, cartoon murder mysteries, again, it's just like murder mysteries. We're going to pull down the title and the year from the movies class because those are the primary keys. We do not pull down length and genre because there are attributes that are not primary keys and they belong with movies. And we do add weapons because that is an attribute that is local to cartoon murder mysteries. Okay. So those are two of the techniques. Let's look at the last technique. So in the last technique, what we'll do is this. We'll look at all of the possible attributes, and we have title, year, length, genre, and weapon. Okay, and we'll put all of those attributes into a single table. Okay, movies. Now, I do lose some information if all I do is that, because now how do I know if it was a cartoon? Well, I used to know because there was a record under cartoons, but now that record is gone, and so there would be no way of knowing. The way that we solve that problem is every time we use the just one class approach, we always create kind of an extra attribute. I usually call it type. Movie type might have been perfectly fine. And that would have the value murder mystery, cartoon murder mystery, or because this is incomplete, it would be other, right? So it could be something other than those three. So that's what type would have. And the way that I would use that type in a program is if type is murder mysteries, then I know that weapon is an interesting attribute. If the type is cartoons, then I will know that weapon is not interesting. It shouldn't have anything in it. In fact, it better be null. Okay. All right, that's subclassing. Now let's talk about aggregation and composition. Now remember, when we talked about aggregation and composition, we made the observation that aggregation means you should have at most one parent because you're part of a hierarchy. And composition means that you should have exactly one parent because not only are you part of a hierarchy, you can't live outside of the hierarchy. So you have to have that parent. Okay. So actually the way that we're going to translate is just nothing more than the cardinality based rule. And really what that means is we're never going to create the explicit relationship table. Remember we talked about that when you had an association, but one of the endpoints is 0 to 1 or 1 to 1, then we're unlikely to create a table just for that. Instead, we will simply move the primary key of the to 1 table and copy it over to the appropriate record in the other table. Okay, so let's look at an example of how this works. We have the same kind of schema, but first I'm going to look at the relationship between studios and movies. Okay, so a studio really just has a bunch of movies, and what that means is that each movie has one studio, and we'll put this in here. So if you look at the movies table, it's got title, year, length, and genre, which are its local attributes, and it also has studio name because that's what links to the studio that it forms a part of. Okay, in the relationship between precedents and studios, a precedent can work for only one studio. Okay, so what we'll do is in the precedents we have the certificate number. We also have the studio name, which points directly to the studio. Okay, so that's how we do it, and this works reasonably well. Now, if you're wondering, hey, that was the same answer whether I used a open diamond or a filled-in diamond, you're absolutely right. The only extra issue is that if you're the president of a studio, then you actually should have a studio name. And the way that's handled is by saying that studio name cannot be null. All right. Now we haven't talked about constraints, so I'm not going too deeply into it. But I'm bringing this as a spoiler right now, essentially, which is that we can specify that certain fields are not allowed to be null, certain attributes are not allowed to be null, and we need this here for the precedence table. All right, the last thing that I want to talk about is something called weak entities. And weak entities is kind of weird because it is a major issue in relational databases, and we'll be talking about it more in the coming weeks. But it really is not a big issue for UML. So I'm putting this in here mostly out of completeness. Now, once I bring up weak entities, then there is a possibility that this notion will get confused with the idea of a weak reference in object-oriented programming. Actually, there's no such thing. So please don't make that confusion. But if you hear about weak references, if you talked about weak references in software design, that's not what we mean by a weak entity. So avoid the trap. Okay. Now, what is the actual related idea? To be honest, the actual related idea is composition. Our filled-in diamonds. And the reason for that is that when you have a class A that owns another class B, then the instance of B kind of belongs inside of A and can't live outside of A. And that's exactly what the notion of weak entity is. Okay, so the notion of weak entity is, for example, what explains your W number. Your W number uniquely identifies you to the University of Wyoming. Okay, but it does not uniquely identify you at Colorado State, right? And if I had a database that had students from both universities in it, then I would say that each student is scoped to the university that he or she is enrolled in, right? And so that's what the weak entity would be. So yeah, we actually already have that notion is in composition. So since we have already talked about how to translate those, then there you go. We'll just use the composition rules. Now, the book brings up the idea that when we have weak entities, we should add this kind of primary key notation to the UML diagram. This is not standard UML. The major benefit of doing that is it keeps you alerted to the fact that if you are going to take cruise and generate the table for cruise, then the number is not sufficient in the primary key. You actually need the studio name as well, and so that's the that's why that's there, and it's a pretty useful thing. So translation is actually the same as we did before. Here are studios, these are crews. Crews have a number. Number's not sufficient to identify them because the number is like 1, 2, or 3. The studio has so many film crews. So what we'll do is studios, yeah, is name and address. Crews, we have number, which is the primary key, kind of the local primary key, but we also need studio name, which is the primary key from studios. Combined does actually make the real primary key of crews, and then we add any other attributes. So that's how that's done. It's actually fairly straightforward, and we'll be seeing weak entities a lot more over the next coming weeks. So if you don't fully grasp that, don't worry. This will come together.